Okay, I'm going to do another Heathkit product exploration here. And once again, I'm going to start with Chuck Penson's excellent book, Heathkit Test Equipment Products. And I'm going to flip to the VOMs chapter, Analog VOMs, Multimeters, and Voltmeters. Now, I've already done an awful lot of meters in this chapter. I've done the IM-16, which was an FET VOM. It could not measure amps. I've done the IM-17, and by extension, the IM-5217, which was just its restyled follow-up. I've done the IM-25, which was their upper end FET multimeter. They call it a VOM here, but it was actually a multimeter. It could measure amps. And now I'm going to look into some of the earliest and just simply early multimeters or voltmeters. I think these all qualify as multimeters. I'm going to do one on the EK1, but I'm still restoring that. I'm going to give the IM-20 a pass because it's not really a VOM. I'm going to be restoring an MM1, and I also have an M1, which I'm just going to clean up a little bit before I demonstrate it. But today's video is on this series of 3 meters that came out in the early 70s. The IM-105. This was the first one of this series that Heathkit came out with. Came out in '71. They carried it for 10 years. It's sort of a classic VOM. And then I'm not going to do the IM-104, which is a slightly fancier version of the IM-105, and it came out a year later, but they only made it for 1 year. It was not terribly successful. And the 1104, which is really exactly the same thing as the 104. For some reason, they seems to have reissued the same meter with a different model number. This one came out in 72. This one came out in 78. Like they had a hiatus of it for a while and then decided to bring it back and had to call it by a different model number so they could claim it was new and get some people excited to buy it. So I'm going to represent all 3 of these with the 105 because they're all fairly comparable. And I believe these are all Weston meters. Just like the MM1 was actually made by Simpson, not just patterned after Simpson, but actually made by Simpson for being sold by Heathkit. And I don't know if this thing was actually a kit or if it's just a pre-assembled thing. That's what it sounds like. I don't think Simpson just made a kit. I think they made the meter and Heathkit sold it. The 1104, the 1105, and the 104 are apparently all Weston meters because at that time Weston owned Heathkit, and even though I haven't found any examples of it, nor do I know the model number, I've read many places that at least the 105 and the 104 were Heathkit versions of a Weston meter, probably with very little different between them. And as you can see when I show the product, especially the inside, it doesn't really look much like a Heathkit. Many things are done differently than the way they would have done them. So I think these are basically rebranded, but at least these were kits. You could actually assemble them yourself. So I'm going to focus on the IM-105. And as it says, it was made obsolete by the clamshell IM-17 in 1970. I'm not sure I agree with that statement because the IM-17 came out at a different date. I think that it didn't come out in 1970. The IM-17 came out in 1967, so I'm not sure how that statement makes sense. And the IM-17 was a solid-state VOM, you know, so, and I don't, it's sort of a cheap meter too. I'm not sure it behaves or performs as well as the IM-105 does, actually, except for, again, not having the high impedance front end. Anyway, it looks to be a pretty solid, reasonably well-designed, serious VOM, intended to be used by actual working people, not just futzing around in their home lab or something. It does say the case was changed from the 1950s Bakelite to the 1970s Lexan. But again, that's a correlation which I think this book makes, and I'm not sure it's completely accurate. It says the case was changed from Bakelite, and I think they're making the correlation with the MM1, which again is this one, the one made by Simpson. Well, it's not just changing the case from Bakelite, it's a completely different meter. Yes, they're both VOMs, that's about where the similarity ends. This would be a Weston design instead of a Simpson design. Everything's different about it except for its basic functionality. And they said, well, it went from black to pale green. It didn't went from black to pale green. The MM1 was black, and this is a pale green one. Leather handle was replaced by a plastic model. Okay, I don't like the correlations being made there. I'm not sure they're actually that valid. Its capabilities are fundamentally the same as the MM1's. Well, that's because it's a VOM. And it gives all the specs here. I'm not going to read them all. Both the IM-105, which is the fancier version, I'm sorry, the 104 is the fancier version, and its upgraded cousin, the 1104, were discontinued, having been swept aside by the IM-2215 digital multimeter. Well, that or some other things. Anyway, enough of the preamble and history. Let's take a look at the actual artifact. So here's the inside of an IM-105. I actually have two of these. This one isn't working, but it's still taken apart more than the other one is, so I'm going to use it for the purposes of the illustration here. The front panel has the knob attached to it permanently, and it has a keyed shaft which goes up and passes through two different gangs of the selector switch, one each on two different circuit boards. This one here is the one that handles most of the meter interconnections, and it has the meter protection diodes here. It has all these plug connectors, which there are several more here. They have letter names like A, B, C, D, E, and F, and so on. And those plug into these posts. They're right around the other board, so that's how the two boards connect together. The various calibrations, well, this is the 0 potentiometer for the ohms mode, and this is a DC polarity select or swap switch. So if you've got DC measurements and you've got the test leads with the wrong polarity, you can just throw the switch. And there's a capacitor here. I think it's the only capacitor in the unit. Anyway, this switch here primarily handles things like how to interconnect the meter itself with various signals coming from the front end scaling circuitry. In some cases you want to connect it in different ways, and that's done with this switch. Also, the two batteries are connected to the meter circuit using this switch. So it does several different things relating to the meter and the power supply, which is only used in the ohms mode from the two batteries. There's one battery here. It's sort of a specialty battery, but it's still available. I'll mention that later. And then a D cell, which sits in here. And it looks like the case could have yet another battery of yet a different style. Not sure which kind. I think they used the same case on the IM-104 as well. And that's evidenced by the fact that there are cutouts for an extra thumb wheel switch and 4 extra push buttons that only the IM-104 has. Although the 104 does not have all these different binding posts for the test leads to go into different positions. It may handle that with additional switching. Anyway, so these are the battery leads, as I already mentioned. There's not a lot of circuitry on this board other than the things I've already talked about. Oh yes, and the bottommost resistor in the shunt used for the amps mode is just this big piece of wire. That would be the 10 amp mode, I believe, that uses this shunt. Everything else is done with various resistors, but those are on the other board, not on this board. And then the meter itself, the movement is here. It's a taut band movement, and it looks like it's hermetically sealed. And there are these 2 posts, and they're not connected up with wires. What you do is you put this board down here, and you run a couple of long screws, which I don't know where they are right at the moment, long brass screws that go in through these 2 pads and make connection. The heads of the screws touch these pads, and then you go down and it screws into those posts on the meter movement. So that's how that's made. To me, it's sort of a crummy way of doing it, because these are just phenolic circuit boards, and there's no support on the board anywhere close to that, so when you tighten them down enough to make a good connection, the board is kind of bowing. I thought maybe there should be some spacers between the boards there, but at least the Heathkit manual doesn't show that there should be any, so I'm not really too sure about that. Anyway, so here's the other board. This is the front end board, the one that does all the range switching and function switching, and it's mostly just resistors. There are a couple of diodes somewhere on here. Yeah, they're right there. You can see the bands on them. One's vertical and one's horizontal. Those are a special type of diode. I haven't looked up the part number yet. They may be germanium. They are there for the rectifier for AC voltage measurements, and they are, according to the manual, selected to have a lower than normal forward voltage drop. And then these 2 pots here are for the high and low AC volts calibration. The DC volts calibration is all done with that other trim pot we already looked at. I can't get the thing out of the box again. Yeah, this other pot, that's the one that's the general calibration for the meter movement itself. It's a series resistor in series with the meter movement, and that's your general cal that affects all functions and ranges. And then when you're dealing with AC, you have to adjust these 2 different trim pots, one at a higher range and one at a lower range. There is no adjustment for current, and there is no adjustment for calibrating the ohms mode. It's all based on component tolerances. So generally speaking, one quadrant of this switch handles each function. So for example, this might be DC volts and AC volts and DC current and ohms. And so you have a cluster of resistors that all end up being either a bunch of resistors in a shunt circuit or a bunch of resistors in a voltage divider circuit, and each function has its own group of resistors. So these go with here, and these go with here, these go with here, and these go with here. And of course, for the amps ranges that are not the lowest amp ranges, but still fairly high, these big bruisers here are parts of the shunt, just like this one is for the 10 amp range. And then progressively smaller resistors as you get into the lower current parts of the shunt. So again, pretty straightforward, nothing very fancy or complicated on this. The meter protection diodes and the rectifier diodes are the only solid state parts in the meter circuit. I found my bag of parts for this meter. There's the screw that holds the back cover on, a couple little screws that hold on a couple of the binding posts which need to be removable. Those are specifically the ones for the two that have that high current shunt on them. And there are the two long screws which separate the circuit boards. I think that the shouldering on these is supposed to limit how far down the top circuit board gets bowed when you tighten these down, but it still bows some. There's the fuse, except for the highest voltage and highest current ranges, in which case you have to move the test lead to a different jack. All the ones in the more normal ranges go through the single plus input test lead jack, and there's a series fuse that affects that. You can see the special socket on the circuit board that goes with that, and then up on the front you can see the special front end part of that jack that touches the other end of the fuse. And these two posts that do not come out are ones that have sort of a Allen or a hex drive like this, and they screw into the circuit board also and have to be unscrewed before it comes apart. And then you've got these four identical jacks which are used for the higher voltage and higher current ranges. And one of the things that's broken about this meter is that these are supposed to solder into the circuit board, and you can see they're broken out. There's one place where a jack was supposed to go in there, and it would be just like this part of it here would go in like that, and then it would be soldered to that pad. And all of those are busted out, so I'll have to resolder those. Another one goes here, another one goes here, another one goes here. So these are all the ones that go at the corners. If I can get all of those things repaired, this meter might eventually work again. Okay, here's my other IM-105. This one I've just finished restoring and testing and calibrating. It's exactly the same as the other one, but without so many broken parts. Although this one did have, not on this board, but on the other board, the one closer to the front of the meter, the actual rotating contact of that gang had come out somehow, been yanked out of it, and it broke, or not broke, but it bent up all of the spring clips from all the different positions that are supposed to engage with it. And I didn't have any hopes that that was going to be fixable, but I was able to finesse it in there and re-bend those spring clips so they would make contact, and it seems to be working. So I also replaced these leads to the batteries because typical Heathkit, they use solid wire for all hookup wire, and that's okay if you're never going to move it again. It's cheaper and easier to solder than would be stranded wire. But for things like this, where when you take the boards apart you have to flex it, I found that those wires actually had breaks in a couple of them, probably from being flexed open and back a few times. Anyway, so it takes the D cell, it's held in place with a pad on the bottom, and then this other battery here, which I'll see if I can pry out of there. Like I said, I was surprised to find that these were still available. A NIDA 208 style battery. It's 15 volts alkaline. Industrial. I have no idea what these are used for. These are both excitation for the ohms function. That's all they do. They don't power anything else. And this is the one that powers all ohms ranges except for the 10K multiplier, the highest ohms range, in which case there's too much voltage dropped in the circuit for a 1.5 volt excitation, so they go for the glory and jump way up to 15 volts. And I don't know why they did it that way, but I don't know, maybe they use a lot of those batteries in other things. I did have to fix one of the posts which had torn out. I forget which one it was now. Probably this one. That looks like the most recently soldered one. The handle is sort of a nylon handle, and it just slips into channels. In the case, and then is held in there and can pull out like that or be pushed back in. It's actually not a bad design for a handle. So there's the front of that. See if I can get rid of the glare a little bit. Okay, so the DC cal is the pot I highlighted earlier, and it's accessible through this hole. It would not be on the IM-104 because then there would be another potentiometer in this hole. They'd have to be accessing it some other way. But in this case, you can get to it by putting a screwdriver down through there and finding the pot. And then the low cal and the high cal are accessible. They're actually on the board that's further away from the front, so you have to go through this hole in the case, through a hole in the front circuit board, and then find the pot on the back circuit board. The jacks are, a couple of them are way up here. These are front panel jacks. And then we've got all the lower jacks. This one fell out. That's this one here. You can see how it has a hex drive. And these have to be unscrewed before you try to take the darn thing apart. And this is how you access the fuse. This is the special one. There's the fuse, so that's how you get at that. I had a heck of a time figuring out how to take these apart so I could service them because I couldn't figure out how to get the front panel off. I couldn't figure out how to get the boards out, and it's because they're all held in by these three guys right here. Well, these two, not this one. And if you don't have those unscrewed, if you don't know you have to stick a hex driver through there and undo those, you'll never get it apart. It's just one of those things that you just have to know. It doesn't say anywhere on the meter, and you probably wouldn't guess it. And then finally, the whole case is molded Lexan, so it's pretty robust. And then the front panel is also Lexan, with all the different ranges and markings on it. And it just friction fits inside this rim here. It doesn't get held in with screws or anything. No, I won't show it because the previous owner, I bought this from, I believe, the son of the original owner. And despairing of ever being able to fix it because I could not figure out why it wasn't working in the ohms mode, and finally realized that a couple of those wires were broken inside the insulation. Anyway, the guy had all his stuff written on here in indelible ink, so I've left it on there. Anyway, so this gets put back on, and then it just sort of pressure fits mostly by grabbing, you know, different areas where it can press against them. Okay, so the front panel's down now. The meter movement isn't very fancy, doesn't have different colors on it or anything. There's 3 different ranges here, one ending in 10, one ending in 50, and one ending in 250. And the ranges progress with variations on those. For example, 2.5 volts, 10 volts, 50 volts, 250 volts, 500 volts. So you always pick the appropriate one. Unless you're using the 2.5 volt AC range, you always use these 2 scales here, the main ones in the middle. You use this one for DC and this one for AC, and then find the numbers that are closest. So they've got the 2 down here, but if you're on a 2 volt DC, then you'd be looking up here for that position. The 4 for AC also corresponds with this point for DC, and so on. You can also measure decibels using the bottom scale, and as I said before, if you're measuring in the lowest AC volt range, then there's a separate scale for that, probably because of the voltage drop of the rectifier diodes. And then there's only one scale for ohms. And with all ohm meters that work in this fashion, the ohm scale is nonlinear. So you start over here on the right with 0 ohms, and you know, it doesn't look too bad, 5 through 10, although you can see 5 is not halfway between 0 and 10, and then 20 is maybe 2/3 the distance of 0 to 10, and 30 is about 2/3 or half, 2/3 maybe of that, and so on. And then you jump twice, you go up to 40 and then 50 in a smaller space, up to 100 and so on. And you have to select your ranges so you stay out of this area where it's very hard to tell what the reading is. So let's, so these extra jacks, so these 2 in the middle, the minus or COM and the plus, are used for most ranges and functions. There's also an output here, which is just the input conditioned by a coupling capacitor, and that's what that capacitor is for on the board. It's not used by the meter itself, as I recall, but we'll figure that out when I get to the schematic description. I thought that it was only used to condition the output here. A lot of meters had that. I'm not sure what it was really for. It's like it kind of took the input, ran it through a capacitor, and ran it out the output jack, and not really much else different about it. So I'm not really sure how you'd use that. Now if you're measuring 5 kilovolts DC, you have to use a separate input jack. You have to move the wire from the plus over to there. If you're doing 5 kilovolts AC, you need to go over to here. 1 kilovolt AC is up here, 1 kilovolt DC is there. So the 2 highest voltage ranges in AC or DC have their own dedicated jacks. And then finally, for amps, you can go from 0.05 milliamps at the lowest range, which is the same as 50 microamps, which is the native current of the meter movement. And then you go up to 1 milliamp full scale, 10 milliamps full scale, 100, 500 milliamps, and then you jump to having to move the jack to here, and now you can read up to 10 amps DC only. If you try measuring AC here, you won't get a valid reading or any reading. There is no provision for rectifying the current in the circuit if you're reading high current AC. Indeed, the current range is DC only. There's no rectification on that at all. They don't say here that it has to be DC, but it has to be. And let's see. So yeah, that's about that. I realized I still had a little cleanup here I missed before. Neither of my IM-105s came with test leads, so I'm pressing into service some cheap Elenco or whatever brand they are test leads from Amazon. These won't take shrouded banana jacks or plugs, and they just take standard male banana plugs. So I'm going to start out with DC volts, and let's see if I can demonstrate that. Okay, so I'm going to drive the meter from my power supply here, and I'm on the 2.5 volt DC range. So I turn the meter on, and I'm going to go up to ½ volt. And where am I on this thing? Since I'm on the 2.5 volt range, I should be looking at the scale that has a 2.5 in it. This would be 1 volt, this is ½ volt, so that's right on the money. Okay, let's go up to 1 volt. Looks like it's right on the money. Let's go to 1.5 volts. It's really good. 2 volts, right on the money. 2.5 volts, just a little bit shy. Not too bad. Now I'll go to the 10 volt range. And now I have to read this bottom scale. And let's see. Well, I have to read the bottom numbers, but still use the top scale, which is kind of confusing. So where it says 50 up here, that mark is 2 volts. And where it says 100, that mark is 4 volts. Which means this mark here is 3 volts. So the pointer is roughly between 2 and 3 volts, and it should be for 2.5 volts. And now it's reading just a tad high, but it's still pretty close to the 3 volt mark. And let's go to 5 volts. And again, you have to keep in mind that this is 4 and this is 6, but you have to transpose them up to these positions. So the meter is halfway between that mark and this mark, which represent 4 and 6 volts. So 5, maybe just a little high on the reading. Let's do to 7. Yep, it's about right. 10 volts, and we're full scale as we should be for the 10 volt range. Go to 50 volts, so now I should be looking at the middle scale, and 10 volts. The 10 goes with that mark there, so it's just a little bit on the high side. And let's just go up to 24 volts. And so we're about halfway between 20 and 30 volts. We have to use these upper marks. So that mark there, just by my fingernail, would be 25 volts, and it's by the mark to the left of that, so that's 24 volts. So that's working really well. I'm not going to go into higher voltages because I don't really have anything to drive them that high in DC without rigging something up elaborate. But let's just check 250 volt range. So again, that would be 50 volts there, and the halfway mark is about 25. So it's reading about 25 for 24 volts actual, but again, I'm not using the right range, so you start losing accuracy when you do it that way. Okay, let's measure some DC milliamps. I've got it on the 10 milliamp range, and I've got the same test leads in the same positions. I have the power supply set for 24 volts DC, and I have it wired in series with a 4 to 20 milliamp current loop tester, just so I can control the milliamps in a low milliamp range. So if I fire this up, this is set to about, give about 12 milliamps now. So let's turn the power supply on, and it's only set for 10 milliamps full scale, and I'm giving it 12, so it's overranged. So let's throw the switch to put it in 4 milliamps. And again, we're on the 10 milliamp range, so we have to use the lower scale but transpose it to the upper markings. So that would be 10 up there. Let's see, did I do that wrong? Yeah, so I'm using the bottom numbering, and 4 is there, but I have to go to the upper scale. So that mark where it says 100 is actually where 4 should be. So it's reading a little bit low, lower than 4 milliamps, but only by just a couple widths of the needle. Now I'm going to turn my knob down here and take that switch off. So I should still have about 4. And now I'm going to gradually increase it until I max it out at somewhere around 10 milliamps. Now all I can do here is go to an order of magnitude higher, 100 milliamps. So now I'm reading still the bottom scale, but I have to go up to here because it's DC. So this mark here by the 50 is where 20 milliamps should be, because this is 100 milliamps here. So so we have to picture this mark here as being 20 milliamps, and that's about 12. Now if that mark is 20 milliamps, then this mark right here is 10 milliamps, and we're 2 notches over that. That would be 12 milliamps, and that's what I should be getting when this knob is in the middle. If I throw this switch here, that should take it to 20 milliamps, and sure enough it does. Once again, I have to use the numbers on the lower scale, but represent them or move them up to the markers on the scale on the one that says DC. So that, where it says 50, is actually representing 20 milliamps, and it's right on the money. If I take the switch off, it'll drop back down. So that's just proof that the milliamp function works on this meter. Okay, to measure AC volts, I've got my Variac set up there, and it's feeding my AC access panel, which has its dedicated pair of test leads going and plugging into the meter in the normal 2 positions. I have the meter set for the 250 volt AC range, and that means I'm going to be using the upper numbers but the lower scale. So the markings will be the ones on this bottom scale, but I have to use the numbers off the top scale. So where it says 2, that'll actually be 50 volts. Where it says 4, that'll be 100 volts. 6 will be 150 volts. So I'll throw the switch here to apply some voltage, but it's set to 0, so we shouldn't see much. Actually, I'm going to re-zero the meter here. It's slightly high, and that might have somewhat accounted for the readings being just a little off. There, I've re-zeroed it. Reconnect the plug, turn the switch back on, and now let's see what happens. This should be somewhere in the 50 volt range. And it is, if you recall, we have to use this scale, but the numbers from up here. So 50 applies to this point right where the meter's at. And that's somewhere around 100. So once again, the number 100 goes with this mark that the meter's right over. So spot on. And this is around 120 approximately. So again, this would be 125 here, but we have to transpose that position down to here. So yeah, it's right about in the right place. So AC volts works. Okay, to demonstrate the resistance measuring functions, I have the meter hooked up to my Heathkit Decade resistance box. Everything is set to 0, so the input, or the posts here, should be shorted. And indeed it seems like they are, because I'm reading 0 volts and then a little bit under. So I have to adjust the ohms adjust pot here until I bring it into 0. And then if I disconnect one of the test leads, it should go to infinity at the left hand side, as represented by that little sideways figure 8. Okay, so let's try reading. We're on the ×1 range, so 5 ohms would be up here. So I'm going to crank the tester up to 5 ohms, and it's just a little bit under, but not bad. I'm going to go up to 20 ohms, and it's doing pretty well. It's just a little bit off. Again, there's no calibration for this. It's all just resistor tolerances, so the specifications are fairly generous when it comes to measuring resistance on this meter. So if you're in the ballpark, that's about all you can hope for. So let's see. So let's go to 50 ohms. Again, it's just reading a little bit under 50 ohms. And if I go up to 100 ohms, it's pretty much right on, just a little bit to the right of 100 ohms. Now if I try to go to 200 ohms, yeah, it's there, but you're getting into a very low accuracy part of the range. 500 ohms. So at this point I could switch to the 10 times mode. So it's reading a little bit under 50. You have to multiply that by 10 to get the 500. Let's go to 700, and again it's just about in the right place, a little bit on the low side. Let's go to 3.5K. Well, it's way too high, so I'll go to the 100. So that should be 30 times 100 is 3K, and 0.5, but you have to keep in mind that 40 is like the next point over, so it's, or 40's here where my thumbnail is, so it's a little bit off. If I go to the 1K range now, what's it doing? It's reading 35. This is 5 times 1K, so that's 5K there. So that's a little bit under 3K. So the accuracy is not that great here, but again, I can't do much about it. Let's go into the 10K range, where it's using the other battery now, so I have to re-zero it. Oops, I need to make sure I go back to infinity. Yeah, and re-zero it because I'm using the other battery for excitation now. Okay, so now let's go to 10K. So it's reading 1. There's 5 up there, there's 1 times 10K is 10K. And I can go up to 40K. Yeah. So it's up around 4 times 10K, so 40K. And if I bring in 750K, so that's 500K up there. And 2 notches above that is 700K, so that's correct. And it's really kind of hard to tell where it is on the meter, but it's kind of a half above that, so pretty close to 750K. So again, within the tolerance of this meter and its components and its age, it's working fairly well in the ohms range. I find it's a little touchy with the switches here. Sometimes it stops working with the switch, and I have to fiddle with the switch a little bit. And sometimes the batteries don't make the best contact with their battery connectors, and that can cause the ohms range to stop working also. But I know if I pop the back off and roll the batteries a little bit, have them find a clean spot on the contacts and mess with this switch a little bit, it'll come back and work again. So everything's back to 0 and it's reading 0. So ohms function working. This meter actually has 4 positions that are off. Anywhere where it's not pointing to a range is off. So fully up at 12 o'clock, at 3 o'clock, at 6 o'clock, and at 9 o'clock are all off positions. There's the beauty shot. There's the Lexan back panel. Somebody helpfully, probably the previous owner, helpfully wrote that the 15-volt battery is a NETA 208, and then he lists Burgess, Eveready, Mallory, Rayovac, RCA, different model numbers for that battery. Very helpful of him to do that. And then there are these 2 little wedges on the sides and a tab here. So the way you have to put this in is to get it down at the back, and you got to keep pushing it forward until it finally goes down into the recess in the back, and then drop in the thumb screw. The original Heathkit tag was just totally trashed. It was all rolled up in a wad, like a wrinkled up aluminum wrapper from a stick of gum. And I unwrapped it and pushed all the creases out and got it more or less back into shape. But the numbers, the series number and the model number, are embossed into the aluminum, and when you burnish it like that, you lose that. So there was only the faintest trace of the model number and series numbers. So I wrote them in with a Sharpie, and then I re-adhered this with some permanent adhesive. So that's what the back looks like. So let's take a quick look at the Heathkit manual. This is not an original manual, it's a reproduction, a fairly good one. I usually get my reproduction manuals from manualman.com, but he did not have an IM-105, so I purchased this one from another place. I think it was Surplus Sales of Nebraska, and they actually have quite a few manuals for discontinued items. And they did them roughly the way Manual Man did it, but Manual Man cleans everything up so there's no hint of the manuals that he copied, that he scanned, ever have been used. So when you get these ones, you see, you know, it's got reproduced pencil marks and things from the original owners following the steps, you know, things like that. But still not a bad reproduction manual. So you start out with the picture of the thing, table of contents, introduction. The Heathkit model 105 Volt-Ohm-Milliammeter is a highly accurate, well, not sure about that, and dependable multimeter which has a wide range of applications. Entirely self-contained, this instrument is always ready for field or laboratory use. The straightforward design and circuit board connecting system provide for an easy to assemble instrument that is every bit as rugged as it is accurate. Well, since it's not all that accurate, that doesn't necessarily, I don't know, marketing is funny. The unit has a basic accuracy of plus or minus 3% on the DC ranges and plus or minus 4% on the AC ranges. Sensitivity is 20,000 ohms per volt on the DC ranges and 5,000 ohms per volt on the AC ranges. The ruggedized taut band Weston meter movement is protected with the diode overload circuit, while the main input connector is inline fused. Effects of temperature changes are reduced to a minimum by the use of a thermistor compensation and low drift metal film resistors on most input ranges. Another important feature is the high impact strength Lexan case qualifier, registered trademark General Electric. In this case, while small enough to be easily stored in a briefcase or tube caddy, that sort of dates it, doesn't it? Contains full-size, easy-to-read scales. So, parts list overflows onto the next page, so basically a two-page parts list. Not a lot of parts, really. Start out with one of the circuit boards, putting all the parts on. There's a fold-out parts identification sheet. Some more parts on that same board. More parts on the same board. Now you put on that big switch, gang, and how to attach certain posts to the circuit board, how to put on the high current shunt, goes on that same board, and then how to put on the posts that interconnect the two circuit boards. A lot of steps about that. And then they have you rubber band you put the posts and the receptacles on both boards, stick them together, rubber band them together, and only then do you solder all the pins and posts. And that assures appropriate alignment. And then they talk about soldering the certain posts into the pads on the circuit board, as I've already talked about in several places. Then we get to the other circuit board, start putting on the parts. And some wiring for the batteries, and the switch and the ohms potentiometer. Then fitting the two circuit boards together. How to put on the front panel. The front panel, by the way, needs to be popped off in order to calibrate it, because you can't access the trim potentiometers from the back. You have to pop this Lexan front panel off. That also mystified me until I obtained this manual and realized you're supposed to push it through from the back to pop it off. There's also a nice feature in the dust shield for the slide switch. And then how to put on the fuse assembly, and there's a thumb nut there, and the fuse holder, and so on. I'm not sure. Oh yeah, they give you a thumb nut. Okay, so that came with the kit. They assume you don't have a hex driver, so they give you a little thumb nut with a hex tip on it to screw those in. I'm not sure where you're supposed to keep those. Maybe that goes into that unused battery holder on the back. And then they have a description of all the controls. They show you how to put the screwdriver through for the DC cal. And they show you the low and high cal pots are accessed. They show you how to put on the rear panel and put its thumb nut on, and how to insert the batteries. You even have to make your own test leads. And that shows you how to do it there. There's a diagram on how to put in the battery labels and how to tuck the wiring for the batteries into appropriate places, and how to use the 2 long screws to make the connection to the meter movement. More stuff on the test leads. Then your basic calibration. You zero adjust the meter, and then they want you to calibrate it off of a particular resistor inside in the meter and use that as a reference voltage. I recalibrated it using an accurate voltage source. AC calibration, you turn it up to the 250 volt AC position, you hook it up to the line voltage, and they talk about putting a waffle iron in it, and it's like, it kind of dates it. In my case, I just set my variac for a couple of different voltages and measured them with a more accurate meter, and then adjusted this to match as close as I could. And then they do say similarly, if you want a higher precision calibration, you can do it a little differently. And then the final assembly. Then it says ohms adjustment here, but this isn't calibration. It's just using the thumb wheel on the front to adjust for 0 ohms when the input is shorted. Then your basic operation, how to read the meter, how to use the scales for AC and DC readings and resistance readings, things I've already talked about, how to do AC voltage measurements, AC and DC measurements, decibels, interpreting the AC voltage reading if you have non-sinusoidal waveforms, a bunch of charts on the meter movement, talking about how to do decibel measurements. Some formulas are given to you. Current measurements, resistance measurements, maintenance. We talk about what kind of fuse you should use, meter window replacement, case and meter replacement, all sorts of stuff. In case of difficulty, general troubleshooting chart. Factory repair service if you wanted. Of course, you can't do that anymore. The specifications, which I won't go into here. Quite a lot of specifications provided here. Probably copied straight from the Weston manual. And then they have the circuit description. And the X-ray view of one of the circuit boards. That's the rear circuit board. And the front circuit board. And finally, the schematic diagram. So here's another copy of the schematic that I got off from online. It's not as good as the quality of the one in the actual bound manual, but at least it lays flat. I'm not going to try to describe it this way because I just hate the way Heathkit insisted upon trying to make their schematics half pictorial, half schematic. It's not too bad with a simple rotary switch like this. You can pretty much figure out which contacts get made. But when you get to something like this, or this, good luck. You really can't correlate the positions and which things overlap which things to figure out how it works. Heathkit did that on every product I've ever seen where they had a rotary switch, and it's, you know, much better to represent those in a clearer way. You know, I don't think it benefits anybody to show them in a circle. Anyway, it also forces you to have clusters of things like this. It's like, what's going on there? Hard to visualize. So I've redrawn this function by function to make it a little easier to discuss the circuit. But I did make some highlights here to help myself remember where common was. You can see common comes in here, and except for that 0.0263 ohm shunt, that is the one that I showed earlier, just that heavy wire shunt, which is not even a component on a circuit board. Nothing else connects to common until it goes up here, and then common gets connected to various places depending on which function and range you're in. And likewise, this end of the high cal, which is used for AC voltage functions, gets connected to a couple of places in only select positions. And then the batteries get connected to different parts of the circuit in a couple of functions, and so on. This one I could figure out just by deduction. This point here is connected to the COM whenever you're in AC volts, this one whenever you're in ohms, this one whenever you're in milliamps, and so on. So with that overview, I'm going to go to the detailed circuitry now. Okay, here's my sketch for the DC volts function. So we have the plus terminal here and the common terminal down here. And then there's also the special 1 kilovolt DC and 5 kilovolt DC jacks. The plus terminal goes through the fuse and through a board-to-board connector, and then onto the common of the main gang that's used for DC volts only. And there are 5 positions of that switch, from 2.5 volts DC, 10 volts, 50 volts, 250 volts, and 500 volts DC. And then this extra 10 meg resistor here goes only to the 1 kilovolt DC terminal, and an extra 80 meg resistor goes to the 5 kilovolt DC terminal. So it's just a big voltage divider here, and any voltage that you applied gets attenuated to some degree or another by these resistors, and the higher the voltage, the more resistors they have to go through, and dropping certain amounts of voltage through each resistor. Of course, they get smaller. The first resistor is 80 meg, then 10 meg, 5 meg, 4 meg, 800K, 150K, and 45K. Then it goes through, it jumps back to the other board. You've got that slide switch, which allows you to flip the polarity at this point. And then basically all you have is the meter itself. And this part is common for every function. This part does not change. It consists of a fixed 1,350 ohm resistor, maybe I think they just called it a thermistor. It's not a thermocouple. It's some sort of temperature variable resistor. I don't think it's a true thermistor, but it has a nominal value of 1,500 ohms, and then if the temperature gets high as a result of a lot of current going through it, then its resistance increases dramatically, thereby choking back the amount of current. So it's a current limiting device. Then there is the DC cal trim pot, 1,000 ohms. I did the calculations, and it's clear that all the other resistor values are made assuming that this trim pot is set to about the middle of its span. In other words, it's going to have about a 500 ohm resistance nominally. And then you've got your 2 back-to-back diodes, just standard 1N4149s, and then the meter movement, which itself has 1,630 ohms of resistance, and it responds to a 50 microamp current through it, giving a full-scale reading. And then finally, after the polarity swap, then your return path comes down here. It goes through one gang of that switch that I talked about already, and then back out the COM terminal. So to simplify this a little bit, let's take a look at the circuit if it was just set to the 2.5 volt DC range. In other words, right up here to the top, so the rest of this voltage divider isn't in effect, it's just this one resistor. So what you end up with then is you've got the 2.5 volts applied here. You go through the range switch, this represents this whole switch here, but in this position. Then you go through that 45K resistor, that's this one at the top of the voltage divider. Then you've got another switch that represents this guy here. Then you've got the 1350 ohm resistor, the 1500 ohm thermistor, and the trim potentiometer that's nominally set to 500 ohms, plus the 1630 ohm meter. If you add all that stuff up, it adds up to about 50K. Obviously it's intended to be 50K, and precisely it's more like 49,980 ohms, but essentially 50K. So you can think of a 50K resistor with 2.5 volts applied across it if you're measuring full scale for that range, and that gives you 50 microamps through the circuit. How about that? And 50 microamps when it passes through that meter gives a full scale, which is appropriate if you're in the 2.5 volt range and you're applying 2.5 volts. I did some more math. I figured out, well, what if you're in the 10 volt range? Then you take that 50K you've got here and you add 150, which is the next resistor in the voltage divider, which equals 200K. If you apply a 10 volt full scale input to a 200K resistor, you get the 500 microamps. If you're in the 500 volt range, you have the 50K plus a 9.950 meg resistor, which happens to work out to 10 meg. 500 volts divided by 10 meg gives you your 50 microamps. And finally, well, not finally, a 1 kilovolt, you've got the 50K again, you've got 9.950 megs plus 10 megs, plus, you know, working your way up the divider, and you end up with 20 megs. 1,000 volts by 20 megs is 50 microamps. And the switch can actually be in any position at that point, because when you're using the 1 kilovolt input, all of these resistors are in series, and you're not using this jack, so it makes no difference which position you select the switch to. Oddly enough, in the operator manual, the Heathkit manual, it says that, yeah, because the front panel is marked 1 kilovolt also over the 50 volt position and 5 kilovolts over the 500 volt position, that you're supposed to also select this switch to one of those positions when you're using these specialty jacks. They don't explain why that is, and I can't think of any reason why that would make any difference, except that maybe they're figuring, well, what if you had a test lead plugged into this plug and a different one plugged into here, and this lead is laying out there loose and you might touch it, or you might just push on the front of the meter and get your finger down into where it's contacting the front of the jack, and that to prevent having a really high voltage there that might shock you, it's better to move the switch to a different point in the voltage divider. I don't know. It doesn't make sense to me, but maybe they were thinking something like that. And then finally, for the 500 or the 5 kilovolt, you add all those resistors up, you get 80 megs, 5,000 volts oh, I'm sorry, it's not 80 megs, you end up with 100 megs. 5,000 volts divided by 100 megs is 50 microamps once again. So very simple circuit, very easy to understand. Okay, here's my sketch for the AC volts. Now the front end of that's exactly like the DC volts. It has a voltage divider with the same number of resistors, same number of positions. It is a different part of the switch, although it still uses the plus jack through the fuse. This is still the same common, but it's a different section of the switch, and it has its own 2.5 volts AC, 10 volts AC, 50 volts, 250 volts, 500 volts, and then you have your dedicated 1 kilovolt AC and 5 kilovolt AC. And the resistor values are different. I think this was 45K on the AC, or on the DC function, and here it's only 7320 ohms. You've still got this meter circuit here, which is exactly the same as it was on the DC volts. The difference is that you've got this rectifier stage here. There's a bridge with 2 diodes and 2 5,000 ohm resistors. Think about this as a bridge. It could be drawn in a bridge shape if you wanted to. So the current goes this way for one polarity and this way for the other polarity. And the meter circuit here is actually connected between this point and this point. So if you wanted to think about it, you could think about it as a bridge like this. Resistor, resistor, the AC applied here, and then the meter being inside of here. That's an oversimplification, but that's basically what's going on. There is a local, again, which only applies to the AC volts. It's a 2200 ohm trim pot, probably intended to be about in the middle for proper calibration. And then there's a high cal, which is actually a resistor and a trim pot in series wired in parallel with the bridge. So it's like this. So some current goes through that and some current goes through the bridge. And by adjusting this resistor, you influence the high end of the calibration, and then you change the series resistance here to influence the low end of the calibration. But otherwise, it's exactly the same as the DC circuit. I wanted to clarify that these 2 diodes are GD510s. These are pretty much unobtainium now, but they are germanium diodes. I looked it up. They only have a 25 volt peak inverse voltage rating, so very low voltage part. Only good for up to 100 milliamps. And being germanium, they have a forward voltage drop of about 0.3 volts, which is roughly half of the forward voltage drop of a silicon diode. So here's my sketch for the DC amps mode. The meter cannot directly measure AC amps. You could probably measure AC amps if you used an external shunt and then use the AC voltmeter of this to read the shunt, but since the input impedance is fairly low on this, it would probably skew the accuracy quite a bit. So not a good candidate for measuring AC amps. So once again, we have the plus terminal with a fuse, and then another part of the switch that once again has 5 positions, and then you've got your 10 amp DC front panel jack and your common jack. And what you're basically doing here, it's again a slightly different way of measuring the amps. It always boils down to using a shunt, so that most of the current you're measuring goes through the shunt, and then only a little bit goes through the meter. So let's look at it when it's in the lowest range, which is 0.05 milliamps, which is another way of saying 50 microamps. In this case, we just come straight in. We don't go through any of these shunt resistors. We go straight through, and we're directly connected into this meter circuit, which is exactly the same as the other functions we've looked at. It doesn't change at all, and you still have the ability to flip the polarity using the switch, and then the current returns through one of those positions of S2, and then back out the common terminal. So, and then this switch up here is also part of this switch, and it's closed in all amps ranges except for the 0.05 milliamp range. So in other words, when we're not using the shunt, this switch is opened up. When we are using the shunt, this switch is closed. Makes sense. So this switch will be open. These resistors do not factor into it. Your input current comes through here, goes straight through, goes through the polarity switch, goes through the meter, and if you put 50 microamps of current through the meter, then 50 microamps will go through here, and then back out and leave and continue on its merry way. Now if you want to go to 1 milliamp, for example, now this switch closes, and now it's as if this point was tied to here. So now your current is coming through here, and it's going through all of these. Well, no, the switch would be here now, so the current is coming in here and going through all of these resistors, and then finally back out. So that's your main current path. And it being a pretty small current, a maximum of 1 milliamp for this range, you put 1 milliamp across all these resistances, and you're going to get a fairly decent voltage drop. And then that voltage is applied to this circuit, which is basically able to register voltage. And if you apply that voltage across this meter circuit because of its resistance, then you get a current flowing through the meter here of 50 microamps if you have 1 milliamp here. So I did an example here breaking it down. This is the essential circuit, the simplified circuit, but still accurate. If you're in the 50 microamp or 0.05 milliamp range, you've got only the resistances. Oops, I forgot to draw a circle around this guy to further illustrate that it's a thermocouple, or a thermistor, or whatever it is. It's not a thermocouple. So if you're trying to drive 50 microamps through it, then of course the meter registers 50 microamps. And all you're doing is adding this resistance here, about 5K, into whatever circuit it is that you're trying to measure the current of. You would have much less resistance if you were using a meter that did not have to drive its meter movement directly. If you had a solid state meter, then you could use much lower value shunt resistors, and you might only be adding an ohm or two to the overall current path instead of 5K. So it does definitely load the circuit down. Now what if we go up to the 1 milliamp range like I was already discussing? So now you've added all of these resistors, that's all of these, between the plus jack and the common jack. So the majority of your current is going this way because all those resistors add up to only 236.1 ohms, which is way less than 5K, which is what this branch of the circuit, this is the meter circuit, what that has. 236 ohms is about 1/19th of 5K, so it's, you know, not 2 orders of magnitude off, but twice 1 order of magnitude off. So another way you could say that about 19 times as much current flows through the shunt as is flowing through the meter, which means, for example, if you had 1 milliamp applied from here to here, going through here, then 50 microamps of it will go this way and give you a full scale reading on your meter, and then the remainder of the current will go through the shunt. And the same thing will happen with higher currents, except you keep trimming off another resistor or 2 or 3 from the shunt as you select higher and higher ranges. Therefore, it has even greater incentive for the majority of the current to go through the shunt rather than through the meter. And it's always set up so you'll end up with 50 microamps going through this path. So again, pretty simple. Finally, let's take a look at the ohms function. So once again, I've sketched it out. You have your meter circuit just the same as always with this polarity reversing switch. You have some cluster of resistors here, but it's not a simple shunt and it's not a simple voltage divider. It's a little more complicated array of resistors. And you have your 5-position switch, but here you do not have any additional jacks to bypass that or augment it. You have to use one of these 5 ranges. You've got the plus jack, goes through the fuse, and it's applied to the common of the switch. Your resistor under test is connected between the plus jack and the common jack. The common connector comes over here and goes in the negative side or the minus side of the batteries, but it depends upon which range. In all resistance ranges, except for the 10K range, this switch is closed, and that's part of that S2 switch that I said is the one responsible for rearranging the components depending on the function. So then it only needs the 1.5 volt excitation to work. But if you're on the 10K range, then instead of this one being closed, then this one's closed, and it brings in the higher voltage battery. Both batteries are common on the plus side, and it's applied to here. And you've got this resistor, which is an 11K plus a trim pot. That's your, well, I should have said before there was no calibration for ohms. There actually is. I misspoke before. And you've got this trim pot, and if it's set to roughly the middle, then it's about 50K. So that's the nominal design point on it. This switch here is another part of the S2. It's closed in all ohms ranges. So what does that actually do? It's a little hard to visualize. So what it really is, let's take a look at if it's in the ×1 range. In other words, where the switch is shown here, the ×1 range. I swapped cameras. This is my shop camera. It has a little dust in the lens. Hopefully you can tune that out. So I've redrawn the ×1 range as following. You've got the 1.5 volt battery. You've got the reference resistor of 19.5 ohms. That's this resistor here. It's the only one that's always in the path. And then you've got that in series with the resistor under test, Rx, between the plus and common terminals, just like over here. So you have a simple path here. The battery's trying to push current through the reference resistor and the resistor under test in a simple circuit. Then across the reference resistor, you have a 61K resistor, approximately 61K adjustable resistor. And what that really is this. The 100K, if it's set to its nominal middle position, would be 50K. Add the 11K to that and you've got the 61K. So the 61K resistor here represents this. And then in series with that are all of the resistors in this circuit, depending on what you have selected. In this case, it's, as I wrote here, it's R10 plus R12 plus R14. That's these three resistors. Because they are part of the path, if you're in the times 1 mode, they are part of the path and they come back to the resistor here. That's the 61K effective resistor and one side of the meter movement or meter circuit. So, and then finally you've got the meter circuit, which, as already described, all those resistors in series with the meter plus the meter itself looks like this. It looks like a resistor of approximately 5K resistance and a meter that responds to a 50 microamp current by displaying full scale. So that's across the 61K resistor, which is in series with the 19.5K resistor, which is what you get again by adding up different parts of the resistors here, and then that's all put across the reference resistor here. So this is really kind of like a potentiometer. You've got the battery across a potentiometer, and this is like the wiper of the potentiometer, and depending on what this resistor is here, it's like moving the wiper of the pot up and down. You get a different voltage. So basically you're changing the voltage across the reference resistor, and then that 61K resistor and the range resistance, which is much higher, it's 61K plus like 19.5K. That's much higher than 19.5 ohms. It's orders of magnitude higher. So this little resistor divider here barely notices these resistors out here. It doesn't really substantially affect them. And then across this resistor you put the meter circuit, which is again looking to register 50 microamps full scale. So looking at this circuit, if Rx equals infinity, in other words, if this is open, then no current is flowing in this path. Therefore, there's no voltage drop across this resistor. There's no voltage drop here, and therefore there's nothing to push current through the meter, and the meter just sits over there at its leftmost position, which is where the infinity mark is on the scale. So it correctly indicates infinity. Now, on the other hand, if you have a short circuit, so Rx is 0 ohms, then all you have is 1.5 volts across the reference resistor, and if you do the math on all these, it ends up giving you 50 microamps through the meter, so the meter's full right, and that's where the ohm scale has the 0 ohm mark. So again, that works. Now what if you went halfway between there? Let's say that because the ref resistor is 19.5 ohms, what if you had a resistor under test of 19.5 ohms? Now your virtual potentiometer here is set to its middle. It's dividing the 1.5 down to 0.75 volts across this. If 1.5 volts across this got you a full scale reading, then 0.75 across this gets you a half scale meter reading. And what's in the middle of the meter movement? 20 is about in the middle of the meter movement. So 19.5 is really close to 20, so you can see how that works. And then it's just different, with different amounts of resistance here, and you can compensate it by changing this value, by moving the selector here and engaging different combinations of resistors to change this value here. So again, fairly simple.